Yeah, I'm sorry for having this abbreviation in the title. So TED, this will be a main point. I'll explain this. This is the abbreviation for twisted, equivariant, and differential K-theory. It just makes too long of a title. We started calling it TED because part of the talk is about how to bring in all these three adjectives into K-theory, and it needs a term. And I admit I'm hereby, or we have been introducing this term. It's not a standard term, but I'll explain it. Right, so it's about K-theory of Cohomotopy moduli spaces. I'll explain that too. And there's some application to topological order. I'll try to give a leisurely introduction of basic ideas. So let me start by recalling a folklore statement that you're all very well familiar with. Many of you will have worked on this. And this is something that has been thrown around in the community for decades already. So the folklore says that topological K-theory, and really in its fully twisted and equivariant and differential form, TD, classifies. And the old statement is in string theory on the right side, stable D-branes, a famous statement. It's supposed to classify stable, possibly non-supersymmetric D-branes. More recently, starting 2009 with a proposal by Kitaev, people have become convinced, I say it this way because I don't think there was really a proof that deserves the name, that topological phases of matter and crystalline materials, as long as they are free, as long as the fermions in the material have an approximation that is, are well approximated as by free fermions, is also classified by some form of topological K-theory. But it is also part of the folklore that this is not actually enough, that there's some enhancement necessary of this setup. So again, on the string theory side, this is an old story. It's known that there is some non-perturbative effect that is not being taken care of by the usual string theory folklore using D-branes. But also on the condensed matter side, it's known, it's clear that not all topological phases of matter can actually be approximated by free fermions. There will be, in fact, it's very surprising that there are any at all that can be approximated this way, because if you have a crystal, the fermions are very close to each other. So it's actually a surprise that some materials do have a good approximation by free fermions. On the other hand, the folklore that K-theory classifies topological phases of matter it doesn't, the usual reasoning does not apply to interacting phases. And it applies so well to the non-interacting phases that it seems to me that tacitly in the literature, people have assumed tacitly that therefore K-theory cannot be used to describe interacting topological phases. And this non-perturbative or interacting enhancement is also known, I mean, this is still part of this folklore. It's known to be necessary, on the one hand, to describe non-perturbative string theory, M-theory, M-branes. And more recently, on the left-hand side, to describe topological order. So these are strongly interacting phases of topological materials that are thought to accommodate, anion braiding statistics. And so these non-perturbative effects are actually thought to be very important for some of the aspects of this whole story that are actually the most interesting, both theoretically but also for applications. So on the left-hand side, these anion statistics have famously been proposed to be a basis for realizing topological quantum computation. And maybe even more striking on the right-hand side, a point that is sort of well-known but is rarely being appreciated is for what it is. The ADS-CFT corresponds in string theory is usually applied in the large n limit, where there's a humongous number of branes, in which case the supergravity approximation in the dual applies and describes the field theory on these branes. But this humongous number is, of course, far from anything realistic. If you want to do ADS-QCD, to use this holographic framework to say something about realistic physics, where n is 3 of the order 1, then the Toft coupling and n will be small, so the stringy effects and eventually non-perturbative M-brane effects will kick in and be needed to describe the field theory. So in the old days of ADS-CFT, this has been advertised the other way around. People said, oh, well, we know what non-perturbative quantum field theory on the brain is. We can just put it on a computer, as people say. We can just run lattice computations. And so dually, this defines M-theory for us. This is a bit of a cheat because there's lots of subtleties to the statement that we know what non-perturbative QCD actually is. We don't. I mean, all the discussion you see in analysis of LHC data is all revolving around unknown hadronic contributions because we cannot, from first principles, compute the actual bound states of QCD. The LHC has been spitting out resonances en masse that nobody predicted because nobody has control over QCD in the non-perturbative regime. So just to amplify that, this is why it's important to have this non-perturbative limit there for practical applications. Okay, so that's the folklore. In one way or other, this is known and has been for a long time. And I just want to amplify that it really is folklore in that, I mean, this is maybe the easiest part in a sense because it's a pure technicality. K-theory in this full, twisted, and equivariant and differential version has never really been fully constructed. Certainly not systematically as a special case of a general construction of twisted, equivariant, differential, generalized cohomotopy theories. There's, of course, a large number of constructions in topological K-theory that combine at least two of these and maybe 2.5 of these aspects, but a full construction has not been, as far as I know, not been given before. And more famously, but maybe less precisely, it's of course famously open what this non-perturbative completion of string theory or of the interacting phases on the other side really is. It's the famous M-theory conjecture that has been around since 1995. People have gotten so used to throwing around the various hints and heuristics that one has that sometimes people tend to forget that this is widely open. It's not known what that full theory actually is. And just to amplify that, you know, completing these open questions is actually crucial for getting to the point of this whole story that actually gets to practically relevant applications, which is, yeah, to hydrodynamics. Oh dear. So let's see, where is this? My screen is still on. Okay. So that's kind of the motivation. It's an interesting storyline, but it has remained open. And so what I want to do kind of boldly here is propose a solution, something that at least looks like a partial solution to these problems. That's something I've been working on with Hisham Sati and others for quite a while now. And I'm trying to survey the 3 ingredients that go into it. So my first claim is going to be, and I'll briefly indicate this, that there is a systematic construction of twisted, equivariant, differential, generalized cohomotopy theories in full generality, in particular of K-theory, which is transparent, elegant, and useful in practice in a context that we call cohesive infinity-topos theory. So that's a general context of geometric higher homotopy theory. So that is a technical, not too surprising claim that amounts to giving some precise definitions and proving some good theorems. So this is, the next point needs more of an inspirational input. So we have a precise proposal for what this missing interacting enhancement is for all the things, at least, that as long as they're not interacting, are classified by K-theory. So this is a hypothesis which we call hypothesis H, just to give it a name. So H is for homotopy or for Hisham, who came up with this first some years ago. And I'll say what that is in a moment. It's actually at the bottom of it. If we ask, what does it mean to have an interacting phase in a topological insulator, it's actually a very simple prescription, but it is part of something larger. And finally, this is something we've sketched out and are beginning to implement now with a new research center that we have at New York University in Abu Dhabi, which was just launched this year. We can put this together. It turns out that this cohesive infinity-topos theory, even though it sounds extremely abstract, well, maybe it's abstract enough to be actually simple again. There's kind of a programming language for doing precise constructions in this context called homotopy type theory. And if you combine these things, you get something that is an actual programming language for topological braid quantum gates, which connects to the actual application. So it's these 3 points that I do want to convey broadly the basic idea of. I have lots of details in the slides, but we'll see how far we get. Systematic construction of K-theory, precise proposal for its interacting enhancement. So for the interacting enhancement of whatever K-theory classifies. and a concrete implementation of the topological quantum gates. So this goes back to an idea I had originally in my habilitation thesis, which was called differential cohomology in a cohesive infinity-topos. There is some abstract context which allows you to talk about exactly these things. Higher homotopy, which you need for describing things like generalized cohomology theories, the differential refinement needed to make them differential, and the equivariant aspect. Without going into any of the details of this right now, this is just the introduction. Let me just highlight what the key technical point is that hadn't been really fully discussed before, or not appreciated for its subtlety. Namely, in order to construct a differential refinement of any cohomology theory, so something where connections come in, the key object you need the analog of the Chan character map, sometimes what's called the Chon-Dold character. The Chon-Dold character maps a generalized cohomology theory to rational cohomology with coefficients. And the differential refinement, as noticed long ago by Hopkins and Singer, the differential refinement of a generalized cohomology theory is essentially the collection of homotopy fibers of the Chan character, or more precisely, the homotopy fiber products of the Chan character with differential form data representing the rational input. So the crucial thing to construct, if we want to set up a general theory of twisted equivariant differential cohomology, is to understand what the analog of the Chan character is in full generality. And this is subtle and was previously underdeveloped because, in contrast to what happens non-equivariantly, the classifying spaces for equivariant cohomology theories and for their twists are in general not simply connected. So this seems like what is a technical point that you might easily want to sweep under the rug, say, okay, maybe we can just go to the universal cover and stuff. But this is actually a key technical point. There's a Galois theoretic effect hidden in this, in the fact that once you are looking at cohomology theories twisted and equivariantly, that everything has a pi1 action of the classifying space. That means that there's a Galois theoretic effect everywhere. Everywhere where previously you just had differential forms, there's now actually a finite group acting. In addition to the equivariance group, this comes from, at each stage in the equivariance construction, comes from deck transformations of the classifying space. And the claim we have is that it's this Galois theoretic effect that is ultimately actually responsible in revealing that there is the structure of conformal blocks, so something that seems very non-abelian, hidden or reflected in that K-theory of certain configuration space. And that is, of course, what is needed in order to find anything like Anyonic braiding statistics in K-theory. So I can explain this, and will maybe. I have slides that explain this in more detail, but just very quickly to highlight what that extra effect is. So in this stack theoretic description of twisted equivariant K-theory, where all objects involved are stacks or orbifolds, it is this very simple picture. We have some domain orbifold, which in this example that I have on the board is actually a trivial orbifold in the sense that we are inside a singularity. The group G acts trivially on everything. So we're looking inside an orbifold singularity for the purpose of this argument, hence this notation. And then there's a universal stacky bundle of Fredholm operators. So Fred is the space, the actual topological space, not the homotopy, the actual topological space regarded as a stack, as a topological space in stacks. Homotopy quotient by the projective unitary group action, that forms a universal bundle over the moduli stack for the projective unitary group. And yeah, it turns out this is really what twisted equivariant K-theory is once you go to this stacky higher topos theoretic perspective. It's just the twist is a map to this moduli stack for BPUH, and the cocycle is a lift of this twist, so a section of the associated Fredholm bundle. And now the point is that if our domain is actually a trivial orbifold, so if we look what happens inside an orbifold singularity, in general this happens all over the place on the orbifold, but inside an orbifold singularity, we have a Cartesian product here of whatever topological space there is inside the singularity and the singular point. And by the mapping stack adjunction, by one of these formal operations that exist in higher topos theory, we know that maps out of a Cartesian product are the same thing as maps out of the first factor into the mapping stack out of the second factor. It's just the usual currying operation. It says a function of two variables is the same thing as a function of a single variable with values in functions of the other variable. But the point is, this mapping space here from BG to BPUH, to this mapping stack, that turns out to be the G stage of the equivariant classifying space for PUH bundles. And that is not simply connected. In fact, for nice enough finite groups, this contains the Pontryagin dual group as its of G, as its fundamental group. So we can inject there, and so there are twists of K-theory now that factor through this inclusion of this non-trivial equivariant group. Then, by general nonsense, this mapping stack image of our universal bundle pulls back, and it turns out that the resulting adjunct K-theory cocycles manifestly have an action, are manifestly things that are twisted by a local system with coefficients in G star. Yeah, so in that, yeah, so G doesn't have to be a Beagle for this statement to work. It can, for instance, be any finite subgroup of SU2, but for the actual applications to anyons, we take it to be a finite cyclic group. Yeah, right. So I'm writing for the, I mean, in general, G star is in general the homomorphisms from G to U1 that appears there. Yeah, but this being the full fundamental group on the stable homomorphism, which I haven't described, holds generally for the Pontryagin dual group. Yeah, I can explain this in more detail, but just to point out, this is kind of the mechanism. There's an extra degree 1 twist when you look at, I mean, K-theory famously has this degree 3 twist, which is the plane maps to the classifying space of PUH. But if you combine the equivariance with the twisting, there's an extra degree 1 twist appearing, and that is the all-important twist we claim that gives rise to further break group statistics effects in the K-theory. Okay, so this was part 1. Part 2 is this precise proposal for an interacting enhancement via hypothesis H. So this goes back to Hisham's article from 2018. It was published then, it was written earlier, much earlier, I think. And the simple idea is the following. Instead of evaluating, so remember both in the classification of D-branes as well as of topological phase of matter, we evaluate, we say the stable objects, the ground states are in K-theory, but in K-theory of what? Usually we take it to be the K-theory of the plane space-time orbifold in string theory, or of the Brion torus orbifolded by the crystal symmetry group. And if you go through the logic of this, yeah, maybe I have a slide for this later on, then you see, well, why is it the K-theory, of course, of the Brion torus? Well, because we're classifying bundles of electron wave functions, of single electron wave functions, which are sections of the Bloch bundle over the Brion torus. Now, if we have more electrons, it will not just be this plane bundle, but it will be fiber product of that. But due to the Pauli exclusion principle, the location of electrons may not coincide. So you see, there will be, it's plausible, at least already on a rough level, that if you want to talk about classifying interacting phases, you need to be looking at the configuration space of points. The space, kind of the modular space of putting distinct points into your original domain. Well, I'll say more about this in a moment, but that is generally the idea. And the interesting thing is, configuration space of points by deep theorems, classical but deep theorems of Pontryagin, Siegel, and others, is actually closely related to a non-abelian cohomology theory that is called cohomotopy. So that's where this cohomotopy comes in. So if one looks at, when you go beyond the Brion torus and ask what is the non-perturbative classification of M-branes in full M-theory, the plane configuration space of points of space-time is in general not sufficient. It can be under certain conditions. The general statement is actually that it's the cohomotopy moduli space. So what is this? So cohomotopy is just a fancy name for homotopy class of maps into a sphere, right? So just as ordinary cohomology is classified by maps into an Einberg-MacLane space, K-theory is classified by maps into space BU, the classifying space of the stable unitary group. You can ask, well, what is classified by any homotopy type? And if you take the simplest ones, the spheres, but if you map out of spheres, you're computing homotopy groups in homotopy theory. If you map into spheres, it's called cohomotopy. So this slide has a bit too much information now here. This statement here is Siegel's theorem, which says that the modular space of cohomotopy, so the mapping space from a suitable domain into a sphere, is actually the configuration space, or is some version of the configuration space of points in that domain. Some technical bells and whistles added. This is an unordered configuration space. If you want to have an ordered one, you intersect two such. And we claim that if you go through this is really a fun exercise. You go through these old theorems, and once you have this dictionary to see how cohomotopy classes map to brane charges, you see that such a fiber product, for instance, of maps into cohomotopy encodes configurations of branes, which can be interpreted as M5 branes intersecting in an MK6, yielding these points, these point configurations, which you can then evaluate your K-theory. So back to the solid state physics, the claim is that if you do the TET-K cohomology of endpoint configurations in the Brillouin torus instead of the Brillouin torus itself, then that classifies the valence bundle of interacting electrons in the approximation where we keep track of n interacting electrons. And in there, then, you find the topological order. Finally, this last point is that, that's what I just mentioned, is that you can now work out, so what is the twisted equivariant differential cohomology of a configuration space of points? If these are points in the plane, it turns out that the Chern characters of the twisted equivariant differential cohomology will now be differential forms as familiar from the image of the twisted Chern character. It's usually taking values in the degree 3 twisted de Rham cohomology, which is twisted by a closed differential 3 form. It's the standard statement. So in this case now, due to this Galois theoretic effect that I mentioned, it turns out that these Chern characters are actually twisted by degree 1 forms. So they're twisted by what's called a local system. And there's an old theorem from 1991 from Feigin, Schechtman, and Vaschenko, which maybe went a little underappreciated. These people showed back then that the space of SU2 conformal blocks for the SU2 affine algebra, genus 0, is actually given by the one-twisted equivariant de Rham cohomology of configuration spaces of points. So that's the connection to the conformal blocks. Yes, it's the, well, it's not, it's the configuration space of, that's right, But I mean for the, And then, so these configuration spaces of points are fibered over each other under the map that forgets a number of points. And then it turns out that the canonically existing Gauss-Manin connection, which tells you how does our TET-K theory vary as we move around the fibers in this fiber bundle, that is the Knislnik Samologikov equation that encodes braid monodromy representation. So in short, what this is saying is that if you do apply twisted equivariant differential K theory on configuration space of points, the values are conformal blocks, and the dependence on the points is just the dependence that you expect for a braid group representation, as should describe Anion statistics. So this is this usual cartoon picture. Think of this square here as the Brillouin torus, cut open with sites identified. And we imagine that there is, in our article we describe this in some detail, how this comes about from the actual solid state physics, but you imagine that somehow there are some points in there that are defects or surface defects for the electron wave functions, so these will be the points in the semi-metal where the band nodes meet, which you have to take out. And then as time passes, you can imagine braiding adiabatically, maybe by affecting a material, somehow adiabatically braiding these defect points around. The thing now is, if you look at this situation now in TET-K theory, then so you evaluate your TET-K theory on this configuration, it gives you, an abelian group inside which you have canonically identified the conformal blocks whose elements, which are identified with Anion wave functions. And so as you braid these around and ask how does my K-theory, K-theory class now depend as we move in this fiber bundle configuration spaces. This will transform, and that transformation is a breakgroup representation for SU2 onions. So yeah, as I already mentioned at the beginning, remarkably, all these constructions, even though they, or because maybe, they seem a bit abstract, there's being developed a programming language for them called cohesive homotopy type theory. And we just got granted a research center to work on this stuff. It's now called the Center for Quantum and Topological Systems at NYU in Abu Dhabi. So the plan is now to put these pieces together. So these are these items 1, 2, and 3 that I mentioned to get a neat software implementation of these topological quantum gates by identifying them with K-theory classes in this cohesive homotopy theory. So let me see how I'm doing with time. Let's go through these 3 items in a slightly more detail in the remaining 20 minutes maybe of the talk. So, oh, I see, okay. Okay, great. So let's indicate a little bit this K-theory construction. So I want to amplify maybe one point here. I'll not go into details of this topos theoretic background here. I do want to amplify the conceptual nature of this construction of K-theory. And an important point maybe to make is that I think if you look at the literature since Kitaev's 2009 proposal for this idea that topological K-theory should classify topological phases of matter, you see that the argument for this is really not very tight. And in fact, 4 years later, when Frieda and Moore had their famous article on the classification of topological phases by equivariant K-theory, if you browse that article all the way to page 57, where they finally come to making the statement, they disclaim it. They say, we do not understand why K-theory should actually classify topological phases of matter. And there is a subtlety involved in that there was never before an argument for the actual group completion. So what Kitaev offers in his article is, with hand-waving, an argument for going to for stabilizing the bundles, so going to Murray von Neumann, if you wish, equivalence classes. But it doesn't actually motivate the anti-bundles, the virtual bundles. It doesn't motivate what these should actually be in the topological solid-state physics. And yeah, one point I want to make is that actually there's an old result. So this is not related to what we did. This is just something we found in the literature. There's an old result in the literature where people actually went and said, what is the solution of the following problem, which seems almost trivial, but it's not actually trivial. You want to classify ground states for the Dirac field, for the relativistic electron, including its positron component. You want to treat it as a free field, so disregard interactions, but still ask for the ground states. So it's kind of, you're doing free field theory. It seems like you're just doing single particle physics. It's not quite. You still have to consider the second quantized theory. And the careful argument reveals that these vectors are described by Fredholm operators. So, I mean, this goes through a long computation of how these vectors are described by canonical anti-commutation relations. But once the dust has settled, you see what these articles are saying is that the free vectors are classified as follows. If you split the Hilbert space of the single Dirac field into its electron and positron component, then it turns out there's a self-adjoint bounded operator of odd degree on this graded Hilbert space. So it has these two components, F and F star, whose kernel and co-kernel are finite dimensional, so that makes it a Fredholm operator. And then the dimension, or these kernels and co-kernels, they are the electron and positron contributions in this vacuum. So this gives a good physics motivation for studying this ZEMO2 graded Hilbert space, complex, separable, infinite dimensional Hilbert space. But the fact that it's ZEMO2 graded immediately implies that operators acting on it don't just form the corresponding projective group, but there's two involutions acting on it. There's one involution which exchanges the two factors, the parity involution, and there's another involution that does complex conjugation. So this is the group of quantum symmetries, if you wish, that canonically acts on a ZEMO2 graded Hilbert space. And And what we can do is, I already showed this at one point, so in the world of smooth infinity stacks, you can form a homotopy quotient of the topological space, the topological stack, if you wish, of Fredholm operators, odd-graded self-adjoint, the way we just had. So of a guy in here, by the previous theorem, classifies an electron-positron vacuum, its homotopy class does. You can homotopy quotient by this group of quantum symmetries that act on it. And if we have any orbifold, denoted by these symbols here, then we can, then a family, an equivariant, G-equivariant family of such Fredholm operators, so something that over each point, say in the Brillouin torus, is such an electron-positron ground state. It's just a map of stacks of this form. And so this fibers over just the moduli stack of just this group here, forgetting the Fredholm operators, that is the corresponding twist. So in stacky language, say in the infinity-topos of smooth infinity groupers, this is the definition of twisted equivariant K-theory. It's really KR theory then, because it involves this time inversal symmetry, homotopy class of that, relative homotopy class of that. And so this is the old idea of Kitaev somehow, going back to Kitaev. The idea now is that in solid state physics, suppose you have a non-interacting system. So you suppose in its ground state, the crystalline material, you just fill up the single electron states until you reach the Fermi energy. And so these single electron states form some bundle, some complex vector bundle over the Brillouin torus. And the idea is, by the previous argument, that in a way, if you start from the physics here, and just go through, say, okay, it's classified by Fredholm operators, so we just parameterize them over the orbifold, then you see, well, the deformation classes of such bundles should be in the Ted K theory of that Brillouin torus, which classifies exactly these bundles. So let me, can I do this here on the, so I continue describing the Ted K theory here, but let's jump to what happens to this picture. It's this was just sort of the standard picture, except for this relativistic enhancement, which I think really resolves this issue of why it's actually K theory that classifies the topological phases. That has to do with this positronic contribution. Let's look at this interacting enhancement. So this is something we have written a long list of articles about, mostly in the string theoretic aspect, showing that this proposal, which I'm presenting now, implies a whole lot of things that have been expected in the string theory folklore. But it boils down to the following really simple, but somehow deep proposal or observation. So interacting n electron wave functions are functions in the space of n points in the Brillouin torus, evidently. But the Pauli exclusion means, so these wave functions of n electrons are linear combinations of what in the solid state physics literature are called Slater determinants. So there's the Pauli exclusion principle, which enforces that the wave function has to vanish whenever the position or the momenta, if we're in momentum space, of any two electrons coincide. But that means that the corresponding vector bundle of n electron states cannot be a vector bundle over the space of any points in the Brillouin torus. It has to be on the configuration space of distinguished points. So the picture is roughly like this, lots of symbols here, but it's just a simple idea that in general, if we do take into account n electron interactions, then we're actually faced with a vector bundle of quantum states over the configuration space of n points. This is a Brillouin torus. This is possibly with some other points, fixed points removed. So in the full story, this gets a bit technical here. I want to maybe skip over this for the moment. In the full story, there are some points that are fixed and other points that are still free to move. Anyway, so in the full match to the anion dynamics, one can actually disentangle this and see there's actually two notions of anions in the literature. There's defect anions and there's actual quasi-particle anions. And these correspond to these two different points, some that are fixed, that are subject to adiabatic movement, and others that are actually whizzing around. Anyway, so the general interacting valence bundle should be a bundle, vector bundle over this configuration space. And so that's the idea, to evaluate Ted K theory on this configuration space of points. But now, so this is not actually how we arrived at this originally. This sounds very simple now. I hope it does, kind of with hindsight. But actually, this configuration space picture is part of something larger, which goes a bit deeper. So there's deep classical theorems, ancient theorems, going back to Hopf. This must be 1920s or something, not sure. Pontryagin, 1930s. And then Siegel, a little later, maybe 60s, who identify or relate the convergence space of points to this cohomotopy theory. So let me just come back to this point. I already mentioned this briefly at the beginning. So remember, ordinary cohomology sets of some maybe compact Hausdorff, if you wish, topological space is equivalent to the homotopy class of maps from X into the classifying space, of that cohomology theory. So every decent cohomology theory has a classifying space in this way. And for ordinary cohomology, these things are known as KZNs, Einberg-MacLane spaces, for historical reasons. And in the same way, we can ask, what if we map into an n-sphere and take a homotopy class of that? And that is something that, Pontryagin started studying maybe already in the 20s. He was apparently slow with publishing his stuff, even though he spoke about it early on in the ICM in 1931 or something, but he was slow with publishing until more than a decade later, Thom comes up with this famous thesis, rediscovering parts of this and generalizing it. And ever since, and then apparently Pontryagin very quickly released lecture notes with more details, and ever since this theory has been known as Pontryagin-Thom theory, but really for 20 years or something, it's really just Pontryagin theory, and it's really unstable. It's not, whereas Thom was focusing on stable cohomology theory. Oh, I don't know that. You mean Pontryagin? Oh, I don't actually know. Okay, that might explain it. Maybe, yeah. Yeah, he has very early. One other problem is, of course, that so very early on he used this relation to cohomotopy. So the Pontryagin theorem, which comes next, which I'll show next, he used that to compute the first stable homotopy groups of spheres, and then he made a mistake, actually, which is, of course, maybe not a good way to advertise your theory. He made this famous mistake. Hopkins and Singer go on about this in their article, which was later fixed, which maybe didn't serve to advertise the machine, but it's actually a great machine. Anyway, so this is just a name. You see, this is a cohomology. So these Einberg-MacLane spaces, they form a spectrum, and you're used to, if you ever looked into generalized cohomology theory, people will tell you, oh, they have to form a spectrum, blah, blah, blah. But of course, that is only if you want your cohomology groups to be abelian and have suspension isomorphisms. But there is perfectly respectable cohomology theories that are non-abelian, that are not abelian groups and have no suspension or not an infinite amount of suspension. The original one is due to Chern, the non-abelian cohomology that classifies G-principal bundles, right? Maybe the first one that is the core topic of Chern-Weil theory. And this cohomotopy theory can be understood as being an infinite higher version of this, in that every sphere is B, is the delooping of its loop space. That loop space for high-dimensional spheres is an infinity type. It's not truncated. So if you wish, you can read this here as first non-abelian cohomology with coefficients in the loop space of the n-sphere. Anyway, so that is called cohomotopy theory, since Pontryagin, I guess. And there's this evident map, since the Einberg-MacLane space by definition has its only non-trivial homotopy group is in degree n, and is the integer, so there's a unique up to a sign homotopy class of a map from Sn to it, and if we push forward along this, if you just post-compose maps from X to Sn with this just generator, you get a comparison map from cohomotopy to integral cohomology. So it's, in a sense, it's a refinement. You can ask, if something is an integral cohomology, it may or may not lift to cohomotopy, and if it does lift, it may or may not lift uniquely. So here's Pontryagin theorem. I don't know, maybe it's really ancient and classical, but it's not. So it's rarely presented in this, what I think is a very intuitive form, which immediately explains how it's related to instantons. So usually when people explain the Pontryagin-Thom theorem, at some point they will mention the collapse map and write some symbols, which, if you unravel them, give really this prescription. So Pontryagin theorem says that if you have a normally framed submanifold, so if you have some manifold and a submanifold in there, and the normal bundle of the submanifold admits and has a chosen normal framing, then such a submanifold can only carry a charge in cohomotopy, which is my brainy language, brain theoretic language, if you wish, to just say there's a canonical construction from such a manifold to a class in cohomotopy. And it's defined like this. So this is a sketch of my ambient manifold. The solid line is a submanifold. And now I'm trying to indicate a tubular neighborhood that has been chosen. And the normal identification means that I have chosen basis vectors here, along which I can move in the tubular neighborhood. I know what it means. As long as I'm close to the submanifold, I know what it means to move perpendicular to it a little bit. And so the prescription is very simple. You think of the n-sphere as being Rn with a point at infinity adjoint. So this circle is my cartoon of an Rn with a point at infinity adjoint. And now you just map every point that is on your brane, on your submanifold, to 0. And the nearby points you map to their directed distance. See, this tubular neighborhood is n-dimensional, so it's exactly something that that's what the tubular neighborhood is. It identifies these neighborhoods with Rn. And then you say, well, as soon as we're far enough, some distance away, then we send everything to infinity. It gives a map from the ambient manifold. So you just everywhere very far away from the submanifold, you send it to infinity, to this point at infinity, which is really just any point on the sphere. And the rest like so. So this gives you from a submanifold with this normal framing, a map, and hence a homotopy class of a map to this sphere, and hence a cohomotopy class. And the amazing statement of Pontryagin's theorem is that this construction, or later of the Pontryagin-Thom theorem, this constitutes an isomorphism between cohomotopy, in this case unstable, non-abelian cohomotopy, and the unstable cobordism class. So you can look at these normally framed submanifolds here. Sorry, these are lots of symbols. This is just now the set of these submanifolds under the equivalence relation of bordism, also equipped with normal framing and compatible with normal framing. So for each of these, you can assign this cohomotopy charge and then in cohomotopy, and the statement is that is actually an isomorphism. That's a bijection. So I'm assuming here in stating it this way, if you look at the full details, this is for closed manifolds. There's a version for non-closed manifolds where you need to add points at infinity. But that's what it is. And so what's usually called this collapse map, I would advertise as being intuitively as being the map that assigns directed asymptotic distance. And then you form the preimage. So that's Pontryagin theorem, and it has a special case that is more ancient. This is the Hopf degree theorem, namely in the special case that you're actually mapping an n-manifold to an n-sphere. It is a simple degenerate but important case. In that case, cohomotopy actually agrees with cohomology, and the Pontryagin construction in that case is the assignment of instanton charge. So I'll try to make a cartoon of that here. Suppose you wanna understand why is there flux tubes in a superconductor where the electric field is classified by BU1, which is a KZ2. Well, inside a KZ2, there is a two-sphere, which is the first cell in the CW construction of the KZ2. And since we're mapping from a two-dimensional manifold, if we're looking at the slice in a superconductor that is usually seen in the laboratory, then we can just as well just map to this two-skeleton. And then we're exactly, even though the whole thing sort of really happens in ordinary cohomology, but due to the Hopf degree theorem, we can actually think about it as happening in cohomotopy. The non-abelian version of this, by the way, plays a huge role in the discussion by Atiyah of the classification of non-abelian Young-Mills instantons. This picture boosted up a little. But anyway, you see that some points will get to be sent to some chosen point 0, and the others to some base point. And the Pontryagin construction says you have flux tubes, you have sort of branes, submanifolds with normal framing sitting for all of these pre-images. And part of the statement is that even though these points are free choices, the number of these pre-images here doesn't depend on the homotopy class. It doesn't depend on which representative in your homotopy class you have. So this shows that even though it has not before really been discussed much in this way, that this cohomotopy thing does have an intrinsic physics. It lends itself to discussion of non-perturbative physics. So this is something that I mentioned briefly before. Later, Siegel in the 60s came and gave kind of a generalization of Pontryagin theorem from cohomotopy classes, where you just go to pi 0 of the mapping space. Yeah, sorry. Oh, sorry, sigma is supposed to be this, does it? Sorry, sigma? S2, sorry, what's the question? What is the normal bundle? So this is, so I see the equation. Sorry, so this is the ambient manifold. It's this plane. And I'm indicating a 3D picture which kind of goes away. So the submanifolds are these points. So there's two ways to look at it. Either you can look at so this is the thing as, okay, I didn't explain this well. So this is the sphere transversal to my strong magnetic field, and this becomes a two-sphere if I as one does, as one has to do, if we demand that the field has to vanish at infinity. So that means that this is really again a slice, of a sphere, of a torus, if you wish. And then this direction is just an R1 factor, which in the homotopy drops out. So I'm drawing this in order to indicate the physics picture, which you would actually see in the lab. You would see a slab of material where these vortices, recursive vortices or whatever flux tubes will form. But the actual classification is by where they puncture the transverse plane, and that's this plane. So these points, if you want to connect to the point-Draghin theorem, you have this ambient two-dimensional manifolds with zero-dimensional submanifolds, which are the points where they puncture. Yeah, this is a good question. I'm glossing over lots of details, which I think we do discuss in the articles, but yeah. Let's see. So Siegel's theorem, and this is important for understanding where the configuration spaces come in. It's already kind of plausible here. You have these configurations of points, but you see under the homotopy class, all you remember is the number of them. So you don't, the homotopy class is just a set. It just says, okay, there's n points, but you don't know where they are, or more importantly, you don't know how they are moving, which happened because we're just going to homotopy. But of course, there's much more structure in the mapping space, the moduli stack, if you wish, and that was analyzed by Siegel and others. Peter May has a hand in this, and afterwards came a lot of other people who worked on this. It's still an active topic, stable decomposition of mapping spaces and stuff. Anyway, it says, so again, there's some notation here, but it says if you take the full mapping space under suitable conditions into a p-sphere whose dimension is higher than your domain Rn or Rd, you don't quotient out homotopy here. You can still later if you wish, but if you don't for the moment, then that space is homotopy equivalent to the conversion space of points in Rp, such that, and then there's some technicalities. The first D coordinates have to be distinct, and the point is allowed to escape to infinity in the remaining directions. So I tried to draw a cartoon of this. Here's an element in this configuration space that appears in Siegel's theorem. So drawn here is an R1 times R1, which you should think of as being a cartoon for an RD times R1. And the configuration is a bunch of points which have to be distinct as you project them to the RD. So these roots here may not coincide. And the points, you can't see this here anymore, but if you go to infinity along this direction, they may disappear. You topologize this in the evident way. Once you think about this, an evident way to topologize this. And then, again, for each such configuration, you have this cohomotopy charge map, which assigns the asymptotic normal distance. So it sends this to a co-cycle for cohomotopy. And the statement is, even without dividing out homotopy, this is a homotopy equivalence. So this is how this moduli stack of cohomotopy includes the full configuration space of points. Here it's still points with some, not exactly the points we expect to see. They come in, as I indicated, when we intersect such branes. So, okay, so that was the math. That's what the math has to tell us about configuration spaces. And now here's this observation, which was Hisham's observation back in 2013, I guess. He noticed that for cohomotopy, if you put n equals 4, is actually a quantization law for the supergravity C field in the following sense. So for any cohomology theory, there's, as I mentioned already, there's a character map, the analog of the Chern character, which approximates your cohomology as good as possible with rational cohomology. So if you do this for K-theory, you get the Chern character. If you do it for ordinary cohomology, you just get the Ram theorem, if you wish. It tells you that a class in integral 4 cohomology, for instance, is underlying it a closed differential 4 form. Or rather, it's the Ram class, which I'm writing as a concordance class here. Now, it turns out if you compute what the corresponding character does on 4, oh, sorry, this is a typo, this should be 4 here. There's analogous formulas for every odd dimensional sphere. So if you do this for 4 cohomotopy, you find that the corresponding form data is now the 4 form that you already had before, but in addition, there's a 7 form. The 4 form is still close as it was before, but now the 7 form is constrained to have as differential the cup square up to some conventional factors, which are kind of important. I mean, at this point, they are conventional. And that, of course, is the famous Bianchi identity of the supergravity C field. It says that the supergravity field, C field is closed as a 4 form, but that it satisfies a funny self-duality relation, that there is also the page charge. So this measures kind of M5 brane charge, this measures M2 brane charge if you integrate over spheres. And this is famously not closed. This is the origin of many of the subtle phenomena in M theory that you can see already at the level of just the flux quantization. I mean, this is just a fact, just a math fact. If you say that a flux quantization law, as you should, is a lift of given Bianchi identities, or an identification of given Bianchi identities as the image under a generalized Chern character of some cohomology theory, then it's just a fact that 4 cohomotopy is a flux quantization law. But that's the correct one, right? Whether the supergravity C field in M theory should be quantized in cohomotopy is not, yeah. This is a rational isomorphism. Yeah, so the way this character actually works in full generality is the cohomology operation that is induced by push forward along the rationalization map of the classifying space. So underlying the statement is the fact that the Sullivan model for the 4 sphere in DG algebras is the differential graded algebra that has 2 generators, one in degree 4, one in degree 7, satisfying these differential relations. Yeah. So in this sense, this commutes. So this is all the natural transformation, which is the generalized character. Yeah. You could put these factors further. You could put K-theory in here, then you would have the Chern character here. Right. So this is a curious observation, and I think it's natural to stop for a moment and say, well, let's see if we can check this. Is this more than a coincidence? I mean, it's just a fact here. So is it a coincidence? So is it a mathematical coincidence? And so that's at some point we started checking. And so it turns out that just plain cohomotopy for application of string theory is not good enough. You have to twist it, which is maybe not surprising since everything is twisted. So you can naturally twist cohomotopy by the tangent bundle since this is essentially the J homomorphism, since the tangent bundle is classified by some orthogonal group, and the orthogonal group acts on spheres by rotations. So if you work out what exactly the image actually is, right, which differential forms, is there certain further constraints? For instance, is there maybe an integral flux quantization constraint that maybe the integral class of G4, is it actually an integral cohomology, or is it maybe in shifted integral cohomology, and all these things you can compute? And it turns out, I'm not writing it here for the purpose of this talk, but as you saw at the beginning, we did check a few things. Go back to this here. So we did check a few things, just working out what does it mean if you have cocycles in twisted cohomotopy and you compute the Chern character and ask what, map it to cohomology, what are the constraints that you obtain by lifting? And there's no way to prove anything as compared to M theory because there's nothing solid to compare to, but there's lots of informal expectations to compare to, and many of them do follow. So that leads to this hypothesis that, that we start calling hypothesis H, that maybe the quantum observables on non-perturbative interacting ground states, such as in string theory and solid state physics, are in the generalized cohomology, particularly the K-theory of twisted cohomotopy moduli. Right, so let's look at this onion braiding, how this comes about now. So I have some overlap here, maybe I'll move about this. So I'll just throw this at you as a fact, which is kind of well known to those who know it well. This goes back to Reed and Moore, I guess, has been followed up by many people. So the idea is, right, so the idea with these anions is that the idea is that if you're in 2D, then certain defects can have monodromy as you move them around, forming break group representations. And that idea goes back to Wilczek and others as a long history, and it took people quite some years to figure out how to really phrase this mathematically. And one precise formulation is that the wave functions, the ground state wave functions of such anionic states with a number of punctures should be elements, should be conformal blocks actually of the correspondingly punctured sphere for the SU2 affine algebra or SL2. And these conformal blocks are, of course, famously known to exhibit monodromy in break group representations as you do move the positions of these insertions. So if we just accept this as a black box for a moment, then the question is, where in K-theory are conformal blocks? So previously there was really no way that you would, right, if you take existing literature on K-theory classifications of D-branes or of topological phases, it looked nothing like conformal blocks. And the claim here is, the reason that you didn't see a hint of it is that this extra degree 1 twist wasn't taken care of. This does appear, there's maybe 2 articles that do see this twist. One is Tu and Xu from, I forget the dates now, who construct the twisted equivariant Chern character using bundle gerbs. They do see these local systems, see this twist, but they don't dwell on it much. It's just part of a long technical article. And then there's Fried-Hopkins-Telemann part, I don't know, 1 or something, where some slightly mysterious remarks appear that do say there should be such a local system twisting the K-theory. But nobody has, as far as I know, put it to any use and try to see what does it imply. What is the corresponding K-theory groups? And so, yeah, so our claim is now yes. So here's roughly how it works. This is the simple idea. So look again at our defect configuration. So this is now our plane. Think of it as maybe being the Riemann sphere, the point at infinity removed. There's these further defects here. And the thing now is, remember, if we want to evaluate twisted equivariant differential K-theory on this, and imagine that this whole thing sits inside a singularity, then there's this degree 1 twist, which is given by some local system, which in turn will be given or may be given by a globally defined flat 1 form. So suppose you choose, well, choosing that 1 form means you have to choose, since it's a flat form, you have to choose its monodromies around the punctures. So if we identify this with a complex plane, maybe I should have written this here, then we use the canonical complex coordinate, and we can encode these monodromies by these prefactors here. So the general form will be sum over the punctures of d log z minus that puncture times some prefactor. The exponential of that prefactor is the monodromy around that puncture. So then there's this famous, or maybe not famous, I don't know, this theorem by Fagan, Shechtman, and Varshenko from 94. There was a lot of activity in the early 90s on this thing. Several groups saw the first hints of this, and then these 3 authors were the ones who nailed it down, I think. And they say, for the case, so I'm splitting this up because there's lots of technical details going to it. I'm stating it for the moment for degree equals 1 conformal blocks, meaning that the conformal weight of the total income, so that, yeah, turns out, you see, there's a global denominator here, kappa, level, and then there's the fractions with respect to that level, which determine our monodromies in Z mod K. So this degree 1 means that if you sum these up, the weights of the punctures, then the total sum is 1 higher than the outgoing, 1 lower than the outgoing weight. So that's degree 1. In this case, we don't need the configuration phase, or we don't need further points zipping around. So then these authors prove, in fact, they claim this is an isomorphism, then the conformal blocks for SU2, SL2, with these punctures is the twisted de Rham cohomology of that configuration here, with twist being that closed form. So it's quite a remarkable statement because it gives a conformal blocks, as you know, but let me just amplify it. Conformal blocks usually introduced by quite an amount of machinery, right? You need conformal symmetry, conformal field theory. Then for SU2, you need a fine Lie algebra theory. So you go through many, many pages until you have the definition of conformal blocks, if you look at the standard text. Here it says it's just that, in this case. So these are genus 0 blocks, one has to say. And it's just SU2, the way I'm presenting it here. It's just this twisted cohomology. But now, this is of course curious because this degree 1 twisted cohomology, meaning that the twist is in degree 1, not in degree 3 as usual. This is part of the chain character of twisted equivariant differential K-theory. For twist given, being now this inner local system given, so you interpret this as the twist, and you say, okay, let's suppose the whole thing is inside an A-type singularity, meaning you're on an orbifold with a trivial Z-mod K or K plus 2 action. And so it sits in there. By the way, the fact that we see this non-abelian anyonic effect appear inside an A-type singularity, to my understanding, this is the first realization in actual math theorems of this folklore in string theory, that you see non-abelian degrees of freedoms on your branes in M-theory only if you put them into ADE singularities. This is something that plays a huge role in standard M-theory folklore, but for which it's really hard to find kind of a really solid mathematical underpinning. And I'm suggesting that is it here, actually. This means we're inside the singularity. It also means, by the way, that all this rich structure appears in a very special case of what that K-theory sees. In general, this need not be a trivial orbifold here. We need not be inside the singularity. We can evaluate that K-theory on more complicated orbifolds. And then we'll give some global structure which restricts on the singularities to these structures. But I'm just highlighting this point to bring out where this interesting structure sits. Right, and the theorem goes further. So this was for degree 1 blocks. So it turns out if you want to have blocks of higher degree, so which kind of means in the CFT language that you have more field insertions running around here that reduce, with lowering operators that reduce the weight of these punctures, then we get all conformal blocks. So it says if you want to have a conformal block of degree n, kind of with n field insertions, then very naturally you have to apply the twist equivariant K-theory on the corresponding configuration space. And you realize that, the previous statement, right, this is just a consistency check on this general proposal for doing interacting phases by passing to configuration spaces. There's also always the configuration space of a single point. There's just the underlying manifold. So if you go to one particle, no interaction, we're always back to the traditional story, just to amplify that, right, that we're connecting to that. Yeah, and I guess I ran a bit out of time preparing the slides, so this is just duplication. So that was a quick version of what I had to say. I guess my time is actually up. I have at the end here, we have a Rosetta Stone in one of our articles, in the last one, where we list how all these things match. But maybe it's a bit tough to go through this on the board. So otherwise, I would just end here. Maybe there's questions. Thanks.